discuss are 3D printing design constraints, so understanding what your printer is capable of, reducing mechanical and soluble support, part thickness analysis, use of SolidWorks Print 3D, and embedding fasteners, and this can be used in the pause function or some sort of post-processing. We know there's been a boom in commercially available 3D printers, and they all print just a little bit differently and they use a variety of materials, and it's crucial to know those limits before you start designing for that printer. Now, one of the things to know, one of those limits, is going to be what is the maximum angle you can print with before it requires a soluble or mechanical support. The manufacturer hasn't shared that information as to what the overhang angle is or at what point supports are enabled. You can always identify this on your own by printing an overhang test. Now, there are plenty of these available on open source 3D communities. You could also always create your own. You could create a overhang test and have different angles or drafts, anywhere between 5, 10, 15, all the way up to 90 degrees in increment of 5, or you could create your own. There's many styles available online. Another aspect of your printer to be aware of is going to be your nozzle size. So it's pretty common that printers will use a 0.4 millimeter nozzle, meaning that it will deposit filament in widths of 0.4 millimeters. And if you were to change the nozzle size, then it's depositing either a bigger or smaller amount. Now again, 0.4 millimeters is fairly standard, but there are other manufacturers that support 0.2, 0.3, 0.5, all the way up to 1.2 millimeters being a fairly large amount of material being deposited. And again, this is something you're going to want to check with the manufacturer. You want to make sure that they support different size nozzles and that you don't add your own size nozzles to your own printer without knowing if it's supported first. Now, for discussion purposes today, we're going to go ahead and optimize the part design. Now, this is a machined worm gearbox. This is actually from one of our online training sessions, our SolidWorks Essentials course. The part has been slightly modified to cater towards the discussion we're going to have today regarding additive manufacturing. Now, once we know what the support overhang angle is, and we also know what size nozzle we're working with, or the other sizes we may have, it's good then to discuss the support that we have and how we're going to use it. Now, there are two primary types of support. One being a soluble support. So this is made of a PVA or a filament that is either water soluble or it can be dissolved in a chemical bath. And a printer will use this as a support mechanism and use another filament such as PLA or ABS or PEEK as the primary material for the part. Now with a dissolvable support, again, you can put in a bath, it dissolves away, leaving your finished item left there. The other solution or the other mechanism is going to be mechanical support. This is printed in the same material that you're printing the item. So a ABS printed item would also have ABS support. And it's a mechanical support, meaning that you can take it and break it off with a pair of pliers or use your hands to take it off. It might leave a little bit of a rough surface, but it doesn't utilize a different print head or a different material. It's all one material, one print head. Now, once we know about those two types, either way, support is support, and it's going to take additional time to print, and it's going to take extra material and extra cost. So if we can reduce the amount of support necessary, so we can control those angles a little bit better, we can eliminate the need for support, which then reduces the print time and reduces the material usage. Now, one of the easiest ways to reduce that support is just the orientation of the part. So orient it for the least amount of support, but also make sure that you're still catering towards the stresses in the part and the orientation you're choosing is going to be best. The other thing is that you want to optimize those overhangs for the support-free angles. We are very familiar with the Mark-forged printers, including the Mark II and EX7. Now, these printers, they both start to enable support. So the Eiger slicing software enables support at 45 degrees. That being said, though, with the overhang test, we've seen positive results at 60 to 65 degrees, meaning that we can print items at a 60-degree angle without any support. Okay. Now, for an example here, we have this overhang feature. I'm going to go ahead and click Next right here in the PowerPoint, and we can see here that what would normally have a certain amount of support underneath it that would then go down to the base plate or the build plate and then work its way up to the feature can be virtually eliminated by just adding a loft. Now, this does add a little bit of extra material, and then you do have to identify if it's going to outweigh the amount of support and the print time. But by having a feature just like this can then eliminate the need for supports. Now, it's important that when you're optimizing a model that you keep the data somewhat separate. You can either do this with multiple files or multiple assemblies. My preferred method is to use configurations, and this will allow you to keep the data standard, so have the original data that you have, and its before state, and then to have a configuration that shows its after or optimized state. This allows for you to kind of go back and forth and see what the changes are from its original state to its added manufacturing state. See what kind of material you've added or reduced, take a look at the strength or simulation data, and by keeping that kind of separate, you can see the clear before and after picture. Now, to get those overhang angles, the ones that don't really need support, if we discussed and found that 45 or 50, say 60 was the appropriate angle, once you know that appropriate angle, you can use chamfers, lofts, and draft commands to type in that angle and create features that don't need supports. So for an example here, I'll go ahead and play in this video. So a couple faces that need supports would be these faces I'm highlighting here. And we can make modifications to these faces so they don't require supports. So we can see steep overhangs right here, a 90-degree overhang. And what we can do is we can have multiple configurations. So in this case, I have its original or its before configuration, and I also have an optimized or after configuration. We'll go ahead and enable that. And here we can see some minor changes to the model. For one, we can see a loft function or loft feature used to take the outer shape and kind of morph it into the body. And you can see there from the side it's about 45 degrees. We can also use the draft analysis to identify if it'll meet those standards. Same thing here, we used a bit of a chamfer. That chamfer can then reduce the amount of support. And same thing for the circular boss on the back, another chamfer of about 45 degrees to reduce the use of support. Now, if you're unsure of where to actually put those features, if you don't know what in your design is going to require support, you can always export it as the primary file for 3D printing, which would be an STL file. You could always export it to your slicer, and then the slicer could then identify the places that require supports. Before exporting to an STL, you can use a series of tools within SolidWorks to identify that. And I will talk about one that does it a little bit better, but I do want to show a little bit of a shortcut for identifying those faces. Now there's a tool called draft analysis, and this is typically for identifying faces that don't have an angle that won't sufficiently release from a mold, specifically plastic molded parts. But we can use this in a bit of a way to identify the faces that require some sort of overhang or some sort of angle to it. Now underneath the evaluate menu, we have the command for draft analysis. And the draft analysis, again, is checking for faces that are perfectly vertical and have no angle to them, but it can also show us positive and negative drafts. So what I can do here is I can actually choose the bottom face as the pull direction or the neutral plane. It's pulling downwards, so what I'm going to do is go ahead and push it upwards. And then for an angle, we'll go ahead and type in, say, 45 degrees. Now, I did change the colors here to be a little bit easier. It's typically yellow, green, and red. But what the blue indicates is the faces that require draft, so they have no draft whatsoever. The green is going to be the positive draft, and red is the negative draft. Now obviously this bottom face here, this is going to be resting on the build plate, so it doesn't require any support. But all the other red faces here, you can see, actually require support. So this is a good identification along the way of just looking and seeing, okay, the bottom of this is going to require a little bit of support, the inside of the hole will need it, the inside of this mounting plate will need it as well. And even if I increase the number, so if I increase it into 60, you can see a little bit of red right here going down. Same thing if I was to increase it to, say, 65, you can see the red decreasing there as well. Okay, so that's one of the tools. I will discuss one that does it just a little bit better too. Now, I've talked a lot about the support overhangs and angles and faces and how to accommodate those, but let's go back to those nozzle sizes. So again, the most common nozzle size is going to be 0.4 millimeters. And there are manufacturers and brands that use a 0.6, 0.8, something a little bit smaller like a 0.2, all over. But again, 0.4 millimeters seems to be a consistent size nozzle manufacturers use. Now, 0.4 millimeters is again a good mix because it deposits a decent amount of material, but again, can still be very accurate in designs. Now, if it's 0.4 millimeters, think of if we're creating a feature that is going to be 1 millimeter thick. To accommodate that 1 millimeter with a 0.4 millimeter nozzle, it's going to have to create a 0.4 millimeter wall, followed by a very thin gap of 0.2 millimeters, plus another wall of 0.4 millimeters, equaling 1 millimeter total. And while this is okay, it might look okay from the external, that little gap in the middle is going to delaminate, and there's going to be little strength in that part, because the walls are now essentially on their own, and that gap isn't providing any strength to it. Now, if we know the size of the nozzle, so if we know it's a 0.4 millimeter nozzle, we can work in factors of 0.4. So if I was going to create a feature, say it's going to be 1 millimeter, I should really bump it down to 0.8 or I should go to 1.2 to keep factors of 0.4 so that there are no gaps. That being said though, a lot of manufacturers do not like to have very small features because they're not strong. So for an example, Markforged, they standardize on having a minimum feature thickness of 1.6 millimeters or 4 wall thicknesses. This is plenty strong and it gets 4 walls that are laminated together and have all the strength they need. So again, look at the manufacturer, find out what the minimum feature thickness they support is, and try to accommodate that and use factors of that. If you're optimizing an existing part and you've been using whole millimeters or fractional values, decimals, whatever it may be, you may not be aware of the minimum feature thickness. You might have it in the back of your head, but you might not be sure if it's following the increments of the nozzle size, or you may not know if it meets the minimum feature thickness of the 3D printer. So what you can use as an alternative is, again, another plastic molding tool just like draft analysis, but this one is underneath the evaluate menu, and it's called the thickness analysis. This will allow us to analyze our part and look for anything that is below a specific value. Okay, so we have the same part from the draft analysis, and on the same evaluate menu is the option for a thickness analysis. Now the thickness analysis will allow me to type in the minimum feature thickness or the minimum thickness I'm looking for, and that's going to color code the model and show me anything that is below or above that. I'm going to go ahead and type in the 1.6 millimeters or the minimum feature thickness recommended. We're going to go ahead and calculate, and it's going to take just a couple seconds to process this. Now we can see via the color coding that anything that is greater than 1.6 is this teal blue, and anything that's below that has a green, red, or yellow. Now if I was to zoom in on this part, we can see that it looks like a majority of the feature thickness has picked up on this brim here. And if I work my way around the perimeter and I hover my mouse on it, I can see it has a feature thickness of 1 millimeter, and specifically around these curves it goes a little less to 0.96. So now that I know that this specifically is a feature that is less than 1.6 millimeters, I need to resolve that. I'll go ahead and say OK on my thickness analysis. I'll zoom into my part, right click, and I'll edit the sketch. Here we can see it's a value of 1 millimeter. I'll increase it to 1.6 millimeters. Press OK, exit my sketch, and now the part should be OK for feature thicknesses. I mentioned before that draft analysis was a bit of a shortcut or an alternative to find those faces that require support. Now there is a better tool to use this, and that's called Print 3D. Now to access the Print 3D menu, it's underneath the File, Print menu. And as far as settings go, this allows for you to envision your part inside the printer and see a little bit about how it's going to behave, how it's going to fit, and the best orientation. So you can always select your printer from a long list of managed favorites. You can orient and scale your model within the print volume to make sure that it will fit your printer and doesn't have to be separated into multiple pieces. You can select other options for the infill percentage, the supports and rafts, as long as the printer is supporting the Windows 8.1 driver. And you can also preview your 3D model within that environment, and that will allow you to identify the faces that require support. And there's even an option to enable the striations, or the lines and layers, so that you can see if something has a lot of curvature and if it's going to show a lot of those lines in the 3D print. And if you were to increase, say, the layer resolution, you would see less of those lines. So let's go ahead and take a look at that command. As mentioned, it's underneath the File menu. So a good chance is, if you've been using SolidWorks for quite some time now, you've seen the Print 3D, but you've never really tried it. And that's because it's been on the File menu, right below the Print command. Within Print 3D, this allows for us to envision our item within the print bed and see how it's going to behave and its best orientation and how it fits at volume. Now there is a long list of custom printers, and every year this list gets a little bit better and better. So I can go ahead and I can manage our favorites, and we can check out some of the printers that are available. So again, a lot of known brand names, and it seems to include a lot of options here. Big Rep, Ultimaker, Digital Metal, Desktop Metal, Flash Forward. It's got a long list of them. Of course, our favorite right here, Markforged. We're working with a Mark II, so why don't I add our Mark II here? Here we can see the height, the length, and the width. I'll add it to my favorites. We'll go ahead and close. And in my custom printer menu options, I have the Mark II. Then what I can do is choose the orientation of this part. So I'm going to say that this is going to be sitting in our print bed with this being on the bottom face. And here we can see it resting inside of our print bed. However, I do need to orient it so it'll fit. So I can do that by rotating it, or I can pick the Orient to Fit button, which then rotates it by 90 degrees. Now in this case, we do not have to scale up or scale down, but it is telling us that the maximum scale, if we wanted to fit this, would be 1.3087. On the next menu, on the preview, we have the ability to see the faces that require support and the striation lines. So from here I can say show faces that require 45 degrees or more, and we can see the yellow faces indicating support's not required, blue indicating the faces that are required. This looks a lot like our draft analysis, but again, it's specifically in a Print 3D environment. The other thing is going to be the layer resolution. So a lot of printers can handle anything from about 100 microns up to say about 250 or 300 microns or 0.3 millimeters. If we're working with the Mark II, the lowest resolution it can handle is going to be 0.1 millimeter. So we can type that in. And we can click to say show striation lines. What this allows for us to do is to see how the 3D printing would look. So we can see here that on the top faces, there's not a whole lot of action, but on the side, we can see those 0.1 millimeter layers. And then on these circular features, we can see that the layers get a little bit wider and farther apart, and you can see a little bit more of the striations and layer lines. This is good to know because if you're working on organic shapes, this could be topology studies, could be simulation data, could be things like computer mice or prosthetics. Anything that has a lot of curvature to it is really going to reveal those lines and those layers. So if you're having a hard time, seeing what that's going to look like, you can always enable the striations options to see what that will look like. Again, here, lucky that we can see that this fits within our built volume, so we don't have to cut into multiple pieces or find different ways to attach it. Now, do notice that there are other options here for Print 3D, things specifically like the file formats, infill, supports, and density. And while those options are available, they're only available for printers that have the Windows 8.1 driver. So if you have a printer that can support the Windows 8.1 driver and can be connected to your PC, then SolidWorks can integrate with that. Now, another good challenge for additive manufacturing and 3D printing is that once you've printed these parts, how do you incorporate them into the rest of your assembly? And that's using fasteners. Now, it's quite often to tap the plastic or to use plastic threads. And while that's an alternative solution, it is not a long-term solution. And that is because the plastic generally wears out if it's being used often. Instead, it's better to use store-bought or standard hardware. Now, one of the best options to put threads into your part is to actually use an embedded nut. So going to the store or going online and buying a physical hexagon or an acorn nut or any type of nut that you want to place within your design and use the thread specifically for fasteners. Now, the two styles of doing this is that you can use the pause function on your 3D printer. So it'll pause the print, allow you to drop in some hardware and then resume. Or the other option is just to do the drop-in, which is that you print and complete your part, and afterwards you have a small slot or channel to drop the nut in and hold it with a fastener. The other option is to use a threaded heat insert. Not so much a pressure one, not one that you would want to put in with a press, but ones that are using heat. This will generally melt the plastic and will also expand when you insert the fastener. If you're looking for these, a quick search online via McMaster-Carr or many other companies are now offering threaded heat inserts specifically for 3D printing or for the plastic molded industry. Just make sure to use one that is meant for that application. Method number one is embedding those standard hardware nuts using the print pause function on most printers and slicing software. Now, this isn't so much a setting on your printer. We're not asking you to stand by and press pause when you see the prime opportunity. It's that within the slicing software, there should be a function to pause your print so that you can add something like a magnet, RFID chip, or say specific hardware, and then resume your print. So typically this is done using information like a layer height or a layer number. And once you input that value and send this off to the printer will then pause. Once the pause function is complete, you can now insert your standard hardware. Now in this case, there's a couple features that you're going to need in advance to work. The first being is that you want to have a cavity in the shape of a hexagon, specifically with the point down so that's unable to rotate when the hex nut is inserted. After inserting the hex nut, you want to make sure that it aligns with the hole and there's no interference. And last, you want to print and include something called the bow tie. I call it the bow tie being that it looks a little bit like a bow tie. What this is for is that after you insert the hex nut, you're going to place this on top of the hex nut, which allows for a smooth, uniform, flush surface for the printer to zoom on. Method number two, which is dropping in a single standard hardware nut, is actually much easier than method number one and does not require a bow tie or any pause function. Simply, you just have to create a channel, again in the shape of a hexagon, that you can drop the nut into. Simply drop the item in, apply the fastener, and it's held in place. If you ever need to service the device or if you need to take the hex nut out, simply remove the fastener and shake the nut out. Method number 3 is threaded heat inserts. Again, you can find these on many online retailers and suppliers. Just make sure that they are for the plastic molded injection parts, or better yet, if they're suited for 3D printing. As far as tolerances and how to insert these, you would always want to follow the manufacturer recommendations and instructions, because the tolerances are usually unique to the build of the threaded insert. When adding these threaded inserts, it is key to have enough material for them to grip and fuse to. So there are settings within your print that allow you to increase the wall thickness. So it could be something between 2 or 3 or 4 wall thicknesses, maybe more. If you think about the size of our nozzles, again, 0.4 millimeters, and then every wall is 0.4 millimeters. Just make sure that you have enough material sufficient so that when you insert your threaded insert or your heat threaded insert, that it grips into the material and can melt sufficiently without going into the hollow cavities of the infill of the part, because then it's not going to be strong if it makes contact with those hollow spots.
So I have an example here of some of those embedded fasteners printed in 3D form, and I also have some floating fasteners as well. For an example here, we had mentioned that you can have a channel with a hexagon point at the bottom. You can place a small hex nut in there with the point facing downwards. Make sure it gets to the bottom. We can see the fastener inside of there, and we can add a small screw here. Other examples include having a countersunk hex nut, placing in the hole, and using a fastener from the other side to secure it into place. There are also examples of the embedded fasteners. So there was a pause function. See a little bit of a line right there. There was a pause function where we inserted a nut, put a small spacer over it, and resumed printing. So in this case, there's a small nut in there. It's hidden, it's embedded. And again, we can add another fastener. Now this is a horizontal example. So this was printed upright like this, and we had a small spacer put on top. As I mentioned before, there are options like using the bow tie. So again, we can have a vertical application, insert the hexagon nut in a hexagon channel, add the bow tie on top, and again, another nice smooth flush print. And again, another fastener can go in there and make contact with the hex nut. And last example is that you can have a small channel such as this with an opening where you can drop a nut in. You can drop it out as well, but it has the flexibility to move up and down with a hole in the slot on the other side. So I can drop this inner slot, point down, add this here, and we can adjust this up and down as needed. Apply tension and tighten. And there we go. So a couple different examples of embedded fasteners. They're easy to use. This incorporates a couple of those examples. Just make sure you use the pause function and check the tolerances on the hardware that you're going to use.
Wrapping up the presentation, I hope you enjoyed these tips and tricks and learned something new. And again, thank you for attending SolidWorks Design for Additive Manufacturing, presented by Solid Experts.